So let's start. Hi, good morning, everyone. My name is Jie, and I work for Huawei. I mainly work on SoC power management, such as some DVFS, turbo, idle states, and some low-level implementation. And today, I'm going to talk about this Devfreq for uncore DVFS. So this is more of a power management stuff. This work is collaborated with my colleague Wang Zhi and Li Wei. Okay, so unfortunately this time I can't join the conference in person due to some travel restriction. So I'm presenting this remotely, and if you have any questions, please shout out. I will stop and listen because there's a delay over the network probably, and then the voice around the room might not be very clear. So let's begin. Okay, so first question, what's uncore? If we just tell it from its name, it's basically any parts apart from the application core. And actually, in general, it can mean all the parts of a microprocessor outside the application cores. But they will be kind of too general. In practice, and like those I/O devices and some peripherals may have their own power or voltage domain or frequency domain. So in this context, we may narrow down to some common components, such as some where am I lost? No, okay. We may narrow it down to some common components, such as level 3 cache, interconnects or buses, or memory controllers. They will exclude some I/O controllers, such as network or PCIe or GPU, etc., because we kind of regard those I/O resources as some application units because it majorly executes the workload for the CPU. It's like some accelerators. Okay. So the second thing is why do we need uncore DVFS? So let's see some examples of the power consumption of uncore. This is just some example data from our chips, and on the left there are two pie charts showing the power consumption proportions of power consumption of some three main parts of the chip. On the two states, one is fully idle, the other one is fully busy, where the CPU is fully idle or busy. And on the left, there is for the idle states, the uncore consists of around 41% of the power consumption, and in this situation, because there is almost no loads in the system, so the CPU core consumes only very little parts, like around 2%. For the fully busy case, the fully busy here, where for the fully busy here case here, we run a core bound workload which execute the which is doing the matrix production here. So it's majorly running the workloads within the L2 cache. So no much memory access across the cache, level 3 cache or DDR. So in this case, the uncore consumes 17% of the power consumption. For these two cases, we don't scale down the uncle frequency anymore. This is just the original consumption of it. So this shows some rooms for us to save power. For example, for the busy for the fully busy case, because it's totally almost totally co-bound, so we can somehow lower down the on-call frequency to reduce some power out of this 17%. If it's a memory bound workload, the consumption of on-call may be larger, but it's probably that we can't lower down the frequency because it will impact performance. For the idle case, it's totally fine to lower down the on-call frequency because it's executing nothing. If we don't run any other workload, the I/O device, so then we can reduce on the on-call frequency safely to save power. The other example is on the right graph. This is a normalized power consumption of the whole SoC across different levels of load, which we do the test by running a spec power benchmark. And there is two comparison here. One is dynamic, and the other is performance, which means we turn it on or off the uncore DVFS. So for the blue line, we turn on the uncore DVFS, and for the red line, it doesn't scale the uncore frequency at all. In this example, it saves 7 to 35% consumption between the load levels from 0 to 50% when turning on the uncore DVFS scheme. And there is no performance loss in this case because the workloads of spec power is quite steady, and you can somehow allocate the workload to a target level, and it measures the throughput, and from the point of throughput, it doesn't have any impact on it. So this is the room, the kind of the room that we can get to reduce power. So the main goal of uncore DVFS from our point of view is to reduce some power consumption with minor performance loss. So we need application to be hugely affected by this, but we just want to get some room, to save some unnecessary power consumption out of the chip. Okay, let's continue. So we are finding some kernel support to do the uncore DVFS. There is some related subsystems such as interconnects, maybe, but as we found out, that's majorly for bandwidth management or QoS management stuff, and some other company may have their own uncore DVFS driver, maybe. And as far as I know, Intel has a dedicated driver which only controls some parameters for the uncore DVFS. So it can allow the user space to set some parameters, for example, the upper and lower bound to indicate the firmware to handle some. Or, for example, you can set some lower bounds, so the uncore won't be scaled too low, and which probably affects performance. Apart from those, we find that one kind of suitable subsystem for doing uncore DVFS, which is DVFreq or Devfreq. From its description, it's saying that it's a subsystem for doing generic DVFS framework for non-CPU devices. This is quite generic actually, because apart from CPU, there is a bunch of different types of devices, and but nowadays the major supported device drivers are like these three types, which are interconnects or buses, and some memory controllers, and finally a bunch of GPU drivers supports. This is at least what we can see from the mainline kernel at the moment. Okay, from the subsystem software framework point of view, it consists of these maybe 5 major parts. The Devfreq core part manages the common process of the Devfreq, and Devfreq has a similar design with the cpufreq. So there is a governor driver abstraction there. The device governor decides which frequency it's going to adjust to, and the Devfreq driver implements how it take the action, and how it reports some information or data to the framework or governors. The different part from the cpufreq subsystem is the Devfreq event. So for the cpufreq, you have some common software metrics, such as the busy time ratio over the past few periods, or the paired utilization value from the scheduler. So you have such common software event metrics from the Linux kernel, while for Devfreq, there is no such common or standard software event for a specific non-CPU device, because they are like kind of implementation defined. So it has a extension of Devfreq events with an aim to collect the level of load for the governor to adjust the frequency dynamically. And every kind of device may have their own event driver, which represents the load and reported to the device driver or governor. So the framework is like this, and we're kind of trying to implement uncore DVFS based on this Devfreq subsystem. Just for just a bit more explanation of this, so we need to explain the what are those existing governors, and for elaborating more on the following parts. So there are 5 governors, open source governor at the moment. The first 3 are similar to the cpufreq, so performance, power save, and user space. Performance and power save set the min or max freq for the driver, for the device, and user space will set the frequency according to a user input. It will take the user input from a sysfs file, and then to just adjust the freq on when the file is updated every time. The 2 different things are passive and simple on demand. The passive governor, we can tell from its name, it will take the action passively. It will follow the target frequency of its parent Devfreq device or cpufreq device. For example, if its parent is bonded to a Devfreq device, it will just follow the current target frequency of that parent device. If its parent is a cpufreq device, it will take the maximum target frequency across all the CPU under the cpufreq policy. So it's kind of a so it acts passively, and it's triggered every time the parent device has a frequency changed. The key one is this simple on demand. Actually, this is the only dynamic governor that scales the frequency based on the load. So based on the load reported from the Devfreq event. And its key formula is like this. It takes the current, the constant is like up threshold minus down differentials divided by 2. Anyway, it's a constant, and then multiply that by the current frequency. And in this formula, the percentage of load is updated from the Devfreq event. So as we said, it's implemented by different event drivers. And this up threshold and down differentials are constants. If the device driver don't set it, it will be a predefined macro. And if the device driver sets it, it will take the parameters from the driver. So, but anyway, these two parameters are not changed at the runtime. So, of course, there is some other corner handling in this governor. For example, when the low is beyond the up threshold, it will scale up to the maximum, and when the frequency is at the maximum, it will slow down the frequency scaling a little bit by this down differential constant. But there are some those are some special handling, but the key formula is like this. Okay. So to summarize, this simple on-demand governor is actually quite similar to cpufreq schedule too, because it's like taking the current frequency and multiplied by a linear scaled parameter of load. So if you don't remember the schedule tool, you will multiply the load by 1.25 and then multiply that to frequency current, and that will kind of trying to maintain the level of load at around 80%. And if you replace these things in the brackets by 80%, you actually doing the same to the schedule 2. So though it's named on demand, it's kind of schedule 2 governor. Yeah. Okay. So based on this background, we are trying to do uncore DVFS for that, and there is some specific characteristics of uncore DVFS. The first one is uncore serves for many components. This is especially true for a server SoC, because we have many CPUs on the chip and many I/O devices and peripherals, and there is even some cross-chip memory access on occasion. There is different NUMA nodes, and so any kind of data passing through this on-call domain will be affected by its on-call frequency. So doing this on-call DVFS is very dangerous because we may easily reduce the performance of CPU or some I/O controllers if the target frequency fails to meet the need of any of them. If like the other application we need more QoS, and its performance is not enough like that. So yeah, we're just trying to reduce some power while maintaining the performance goal. So this is one key part here. The first one we are trying to see is, does simple on demand work well under the current scheme? We test this by just a moment. Does anybody have any question for the background up to now?
Maybe I have one question. So you're speaking load for your device. So which metric do you use to compute the load of a device? Main goal is to select a frequency for your core device, but how do you compute the load?
Yeah, this is very much implementation defined. For the moment, we like import the data from some on-chip on-call PMU. So there is some events in the on-call PMU we can interpret from, which kind of showing the loads of the L3 cache or ring bus, and we can take that as kind of a load for the government to do so. And some other device driver will have a similar approach, but we just don't actually know the meaning of their events. For example, like Exynos bus will have event driver. Sorry?
Because you're speaking about the L3 cache, about the interconnect, which are mainly what you want is to provide some bandwidth between one core and the DDR, or between L3 cache and another node, which really look like a memory bandwidth. I wonder, have you looked at the interconnect framework that enable you to set some bandwidth constraint between all your CPU and device on your whole system as a way to get metrics?
For our chips, we don't have like such dedicated metrics. So we are trying to do so, but it doesn't have such dedicated metrics that matches the government design perfectly. And we are just trying to find some useful events that can kind of represent the load level, or represent some load level that you can that it doesn't affect the performance. For example, when you keep some load level below for example 80%, it may have plenty room to serve the CPUs for the CPU to access memory or access I/O resources like that. And we're trying to do such load detection. Yeah.
Yeah.
Okay. So let's move on. Okay, there's one example here. No example, really. Some findings here. Does the simple on demand work well We do a experiment. We did an experiment based on that governor, and it's like this. We first we found a pre-calibrated workload. So for this workload, you will have you will have it can we can lower down the on-call frequency to a specific level, and then you will reduce some power, and then have negligible performance loss. And we kind of implement the event driver as we talked about. So an event driver to detect the utilization of the L3 cache and the network on chip, for example, and put that into this framework, and we set the simple on demand. Here is a trace of results for when setting on simple on demand. So there is two traces. One is this percentage of load. The other is the target frequency. It's the governor requested in this period. The x-axis is the sample. So it's just a time series of sample we trace from the governor. And the key thing is we observe frequency bouncing. It's like a ping pong effect. It just bounces between the minimum and maximum frequency, which is exactly not what we want. Absolutely not what we want. And why this is happening? What we can see is the simple on-demand governor is sort of too aggressive when scaling down the frequency. Just to jog the memory. So when the percentage of load is too low, for example, like 0, you will this formula will scale down the target frequency to the minimum, and when it's very high, you will scale up multiple times. Yeah. So there is no any not much protection for it to scale down gracefully or gradually. Yeah. And this is the first thing I think causing this phenomenon. And the second thing is the load, the metric of load is kind of scaled with the frequency together. I think this is similar to the CPU case. So when you have a steady level of load, when you increase the frequency, so the utilization will decrease very much. And when you lower down the frequency, the utilization will go up. I think this is quite similar to the CPU case, but just this is just a characteristics of it. I think this is not a big problem. The big problem is when it's too aggressive when scaling down. So then we try to write some new governor. Yeah. And okay, so what kind of governor do we want? Do we need to do the uncore DVFS? This is what we can think of. So for this uncore DVFS case, we need some strategy to scale up the frequency rapidly, and when the load goes off, it should be kind of conservative when scaling down. So in order to just preserve the performance, so when the load comes up increase rapidly, we just scale up the frequency rapidly to match the load. So this will prevent some performance bottlenecks when the load goes off. We kind of do that. We're kind of trying to do that gradually and conservatively to just in case that the dose will return in a short time. So, and also to avoid the ping pong effect. So the performance will be preserved. The main behavior for this governor is like this. That's what I think of. Yeah. So for achieving so, we did this kind of a PI governor, which is proportional integral governor. There is some traditional PID governor in the industry, but I don't think the derivative terms is useful. So just take the proportional integral part. And this is kind of a tweaked PI governor because we only use the proportional part for increasing and only use the integral part for decreasing. So we can just ramp up quickly when the load increases and then goes down smoothly when the load reduces. So the benefits of this kind of combines the combine the high responsiveness to the increased load with some stability to maintain the frequency when the load goes off. Okay, and now the trace looks like this. And so the load is not the load and target frequency is not bouncing anymore. Kind of like the load is maintained at a level around 20%, maybe with some spikes to reach to 60% or 80% like that. But the on-call frequency is preserved around 8 or 900 megahertz, and in this case the performance is not impacted, and we save some like 1 point some gigahertz of frequency and reduce the power consumption. And this is just a example. I don't. We may. There might be some better solution to this, and we may kind of want some suggestions on this for doing this uncore DVFS to save the uncore point. So, if there's any other suggestions, please shout out.
I have one.
Yeah.
So you've mentioned this PI algorithm. The T stands for the derivative. So that would be, you might even get the prediction out of your workload. So if you implement the full PID algorithm and then train the coefficients properly, then you might avoid those small spikes or on the plot. You might go even farther with this, but this is the exact remedy for the plot when you are jumping around the frequency, and then you affect your load. So your load is down, then you go down with your frequency, and then you go up with the load, and then so the PI should be good for your workload, but you might still experiment with the D. I would recommend it. Experiments for the thermal governor, and if you have a good known workload, you optimize the coefficients for those workloads, then you might get even better results.
Yeah.
And also using PID is probably better than PI, I agree.
Yeah.
But then you have to tune your parameter of your PID,
Yes,
and which is known to be a nightmare.
Well, it depends. If you know the workload, they mentioned something about the servers. So it's about the interconnect in the servers. So if they know the workload, they might get farther with that.
maybe that will work only for one workload then.
Well, the code can be generic, it can be parameterized like IPA.
I think that they also could try to scale the load with the frequency. Currently, it's not the case. I think it's not scaling variant right now because the spikes follow the frequency dips.
Yeah, so the way how they derive the load metric.
Yeah,
that's interesting. Yes.
Yeah, scaling the frequency, like the bell.
Yeah, the spike might come from the workloads. The workloads might change rapidly. Those are not necessarily coming from the frequency scaling. And I think by implementing a PID governor, you will be more generic. So for some device driver, you can just set the KD to 0, so you don't use that. And then for some other device, they can tune their KP or KI based on their platforms. And yeah, we can have a try. Yeah. Maybe that's also useful in that case. Yeah, there might be one problem here because the KP and KI will kind of they are kind of constants at runtime, right? And then for different workloads, we may kind of need to tune that a little bit, but there is no runtime solution to do so. For the most we can do, we can just report some constant parameter from drivers, but we cannot tune that or let it auto-tuned at runtime. Yeah, that might be a kind of a problem. Yeah.
So here is a question: when you say the governor works well, but from the load there is spikes, while for the target frequency it is not following at all. Why do you say it is performance good?
Because we can get the performance results. For example, if we run this this kind of this load of spec power, we can get the performance value. That is the throughput value from this benchmark. So we can observe that there's no reduction in its throughput. So so this load is just a metric during the process. It's just for scaling the frequency. It's not the final performance value. So if we look at the final performance value in this test, it has no impact.
It's probably a load at that current frequency. So the moment if you don't hit the 100%, so you are saturating the bus at that frequency, then you are okay-ish. In the previous, they had the big bump to 100, and then they raised the frequency, and they saw a low load because the frequency is too high, and then you observe that too high frequency and a very little load, and then you scale down. But and that's why you start this jumping around.
So no means new.
Well, this
no jumping frequency. So for this one?
Yes. So this one, it looks like this 20–30% of the load at the right frequency. So around 900. That's enough for performing the benchmark.
Yeah, maybe the performance, the targeting for the performance is not the best of the hardware throughput in this case. So I don't think it's a good result to indicate it's a good governor then. The frequency just stays here and it is not reaching the highest benchmark of the hardware.
Well, it depends of the benchmark. So we don't know what's the device. Is it an interconnect or S3 cache?
Yeah, well, in this case, we have the L3 cache and interconnects like buses and some memory controllers under this uncore domain.
So if that benchmark doesn't utilize that much the memory side,
it uses, but the benchmark it can control the level of load, right? It can just run a small small amount of utilization.
yeah, but this is not like a benchmark heavy loaded for the memory subsystem like LM bench. So it's not all the time the memory.
I think it has some memory access. Actually, this is running spec power, so it has some memory access. But when you lower down the target throughput, it doesn't use that much. Yeah.
So it's workload specific, and this benchmark probably is not that heavy.
Yeah.
It is getting the job done. You lower the frequency, you increase the utilization, but it's completing the work.
Yeah.
And also I would be curious to see the CPU load or CPU frequency.
Yes.
Associated with that, because what you are showing that is really, I was mentioning this interconnect framework where the goal is really to say the CPU need, I don't know, 1 GB of memory bandwidth between CPU, L3 cache, interconnect, DDR. And if you have another CPU, then you can specify the peak and the average. So you can sum the average. You can ensure a best quality of service from the latency and so on. So I'm not sure. I would be curious to see if just having some static configuration of the bandwidth according to the CPU frequency would reach exactly the same and maybe the better result.
So you already said that configuration. So this interconnect framework is mainly for known devices like display and then camera pipeline, so ISP. But for the CPU, it's hard to predict.
So CPU already are also using that to at least ensure a flow bandwidth
for no workload.
Yeah.
But for some generic purpose, it's hard to predict how much memory you would use. Workload from.
Then you can still add a monitor on this on top. But my point is that the load is really an opaque value, so it's quite difficult to understand what it means.
Yeah, it is hard to understand. But for the interconnect, it's mainly for I need these guarantees for bandwidth for my display, camera, whatever is there.
But the CPU also using that, and the results are pretty.
If you switch to that configuration mode, like a Zoom call or a camera recording, then yes. But if you have this for the generic purpose, any workload, then that would be hard to start.
I would be curious to see that.
I think also to add on what Vincent is saying is that adding two control loops is usually not like a recipe for very fast reaction times. Whereas if everything is indexed on the frequency, then basically there's whatever is already controlling your frequency, let's say schedule two, and there's like the one loop to tune, and there's no risk that you're gonna try to work at different time scale, or one would slow down the other in practice.
I mean, I can easily imagine the cpufreq driver that can get access to the CPU, GMU, IMU, whatever, that can add on top of its interconnect bandwidth some. I mean, you ensure a flow bandwidth because you know that you need at least this value at 1 gig, 2 gig, or whatever, or you don't need more than that at 100 megahertz. And then you can still add if you see some real increase, but at least you have some immediate reaction to any frequency change. Because the main problem there is that you are reacting. So if you have a burst of activity, it's already too late. And if it's only burst, you increase once it's done, and you slow down once it's increased. So
yes, but the interconnect is not the best choice. We will have a talk with Chris Redpath tomorrow about this. Okay. So this is about, we are proposing something like latency-based QoS. And this is about the L3 cache problem. So you are reacting for something happened in the past. You get the load from some average, and then it's already done, maybe. And then you bump the frequency, but it's too late. So we need something like a hint that the workload is there already in the enqueued in the run queue, and then please, whatever it's configured, like interconnect, please now apply this setting, because we know upfront that there will be this bandwidth need or latency need. So it's
the interconnect bandwidth, you can have how many consumer as you want. So you can have an external monitor that adds some additional things that.
But it's not triggered currently from your run queue.
Sorry,
it's not triggered from your run queue like schedule queue. When you enqueue a task in the schedule queue will update your settings. Basically, you can't mean works like that. Interconnect doesn't work like that currently. This one, it tries to compensate.
Sorry, I'm not sure, because UClamp is already used with the schedule queue.
Yeah, that's my point. So UClamp works like that.
Yeah.
But interconnect framework doesn't work like that.
No, so okay, I'm not sure to get your point.
So I mean, the interconnect is just kind of static configuration.
So it's used as a static, but nothing prevents you to adjust dynamically. I mean, it's just collecting and aggregating all the constraints on your L3 interconnect DDR, and you also take into account some other device on your interconnect, and not only. I mean, you see, at least you have a clear picture of what is really needed and what need to be dynamically adjusted.
It's not there in the interconnect console yet. It's
no,
it's more static.
I'm pretty sure that some are using with the out of tree driver. I mean, you can the driver can set whatever and how many times you want the bandwidth that is required. Right now, it's pretty simple to say for 1 gig, I need for 1 gig for the CPU, I need 1 gigabyte of peak bandwidth, and that's it. That will just ensure a minimum bandwidth. So you will not have to wait for your Devfreq to discover that finally now your bus is overloaded and you need to increase. And then if you need further, you can still increase.
Yes, but that's in theory, but in practice, it's hard to derive that, the bandwidth that you need at that workload.
So for like display, you can figure out your bandwidth based on your resolution and your FPS, and that was a way to get the right bandwidth you need. So that's an example where you know exactly how much bandwidth you might need for based on, you know.
So the bandwidth is one thing.
Right.
So this is the throughput, but how about the latency? This is not the bandwidth.
Latency, that's...
You need the latency to complete to get
yeah, that's
fast.
The interconnect gets two values, the peak bandwidth, which give you latency, and the average bandwidth, which give you how sustainable the bandwidth need to be done for the CPU. You have several, you can provide several metrics. It's not only an average value.
It's called bandwidth. It's not called latency, right? It's a peak bandwidth.
Yeah. It's called peak bandwidth, but it's a latency requirement, and it's poorly named.
Okay, poorly named. Okay, so we can rename that maybe.
Question?
Sorry, G, just to tell you that you have 5 minutes to.
Okay.
So, yeah, we can take more questions. I guess you choose what you do if you want to complete the presentation, or if you're okay with questions, just tell us.
I just maybe just 2 minutes to finish the presentation, maybe.
Yeah, go ahead.
Yeah. So the first part is about the governor. So the second part is mostly about the software framework. So at the moment, the governor is quite tightly coupled with the drivers or event drivers, because Devfreq from its own property takes the driver-defined events rather than like common software metric, as I said. So the device driver registration API will have this suggested governor and a dedicated data for the governor passed through the registration API like this. And so it's kind of tightly coupled, and the governor will like this governor will interpret the driver data as its own tuning parameters, like you can set the up threshold on demand, and for the time being, switching or adding some new dynamic scaling governor is not supported, because it has only two dynamic scaling governor, which is on demand and passive, and in a framework it forbids switching between simple demand and passive, and so it only use this data for its own governor. If we want to extend this data for different governors, that's not supported at the moment. So there might be some software refactor or rework if we need to add a new dynamic governor or new scheme for matching for setting different governors for one device. Yeah. So maybe add a new callback for that. This might be a solution. Like for example, add a set governor callback so the driver can set the data every time when they change a governor. Might be a solution, or let it be. The second one is let it be. Maybe it's just fine to let them couple because yeah, because the event is kind of dedicated for the governor, so maybe it's fine for just Devfreq for Devfreq. Yeah.
If you want to make any changes, just send patches and we can discuss.
Sorry?
If you want to make any changes to the code, just send patches.
Yeah, yeah, cool. Yeah, there are some future works, maybe just to list some future works. So there might be some common event description or definition. Because every Devfreq event is having their own one. Maybe if we can have some common architectural description for that, so the software framework will be easily to design. Or maybe we can add some hints from CPU or IO devices as mentioned before by one of the audience, and maybe we can better structure the governor driver data interface so it can matches better. Yeah, and that's all for the presentation slides. Yeah.
I think we have 4 minutes for half a minute for a question.
I had a quick question. So as the requirement on this uncore frequency seems to depend heavily on what you're scheduling on the CPU. So is there anything that tries to do something like per entity, per scheduled entity tracking of this load? So the load you are tracking that you showed in the pictures, they are from the CPU, right? Or can you do that? Can you associate it with the entity you are scheduling so that, you know, if the scheduler knows that you are context switch into a different process with this completely different requirements,
yeah,
anticipate
yeah.
the frequency switch on the uncore or something like that?
Yeah, we kind of adding some topology information of from the uncore device. So when we register the device, in our driver we reports the related CPU to this uncore domain. So when using this related CPU information, you can take the maybe take the utilization values from scheduler. So we can use the CPU utilization for scaling this uncore domain somehow. Maybe that's workable. Yeah.
All right. Thanks a lot, Jie. Great job. You also managed to spark a lively discussion, so that's really appreciated. Thank you.
Thank you.